in the last chapter, we were trying to define the probabilities of certain events. Now we are trying to describe the probability of random variables, but we're still describing the same thing, which is probabilities. So if you recall last week's chapter, we had probabilities, we had also joint probabilities, we also had independent events, and we also had conditional probability. Is this going to come up again this week? Yes, unfortunately, all of those friends are going to come up again in this week's chapter, starting from jointly distributed random variables. So as with events, what if I have more than one random variable? I have one or two random variables. For example, I would like to describe X as the average number of cigarettes smoked daily of someone, and Y is the age at which an individual contracts cancer. So in this type of experiment, I have two random variables, which in my head, I think they're related. So I want to now describe the joint probability of these happening. Like if the average number of cigarettes daily, like for example, on their own, I could compute. Let's move this over, sorry. On their own, I could compute the probability of someone smoking two cigarettes daily. I could compute the probability of someone smoking 10 cigarettes daily. I can also compute that the age at a person contracts cancer is at 18, or maybe the age that they contract cancer is 68. I can individually, I can define the probabilities of each X and Y. But jointly, what if I want to know what's the probability of someone who who smokes 2 cigarettes a day getting cancer at the age of 35? AKA, what's the possibility of this happening at the same time that also happens? So if I'm assuming discrete random variables, I can define this using the PMF. Recall that we have the probability at exact numbers, right? So here, if I wanted to define the joint probability, so if this is one value, then I only have P of a certain number is the probability my random variable equals that number. But if I have two random variables, then I have to define the probability mass function of a certain number and B. In this case, this particular case could be written as the PMF of 2 and 35, which is the probability of the first random variable equaling 2 at the same time the second random variable equals, what's the number I use? 35. Where for all possible values of X and Y, the sum obviously has to equal 1. That is the rule that we already proved in the axioms probability. The maximum number of everything, the exhaustive collection of all of the possible outcomes must equal to 1. So here I can compute the probability as follows. This is just the derivation, since the PMF should be the union of all possible events. Then the probability is also a sum of all of the probabilities. In other words, in the terms of PMF, here's the joint probability mass function of the joint PMF. I can have the PMF of 2 variables, and I can define, I could compute the probability of each individual random variable from the joint random variable. So if I knew the joint random variable, I could compute the individual ones on their own. So you know that we have more than one way to describe probabilities, right? So we also have the joint cumulative distribution. We have the CDF. And in this case, we have the joint CDF, in which when I say the joint PDF of A and B. I'm talking about when this particular condition in which X, the first random variable, is up until A. Remember, that's what the cumulative distribution is, right? All the probability of having the value, all of the values up until a certain number. So here, the probability that random variable X is lower and equal to A at the same time is equal to value B. And thus, if we are talking about a joint one, if I know the joint random variable, if I know the joint random variable, the joint CDF, then my logic is, if I want to compute a singular CDF of X, for example, I don't care about the value of Y. And thus, when I want to compute the probability of X only, I don't need to put a limit on Y. And the other way around, when I'm trying to compute the probability of Y only, I don't need to limit X, because I don't care what the value of X is. So the fx of a certain random variable would be the function of two random variables, where the other one is infinity. So for discrete random variables, by definition, we have this random variable of CDF of the joint A and B, as well as in discrete cases, we can bring it down. Remember, it's possible to get the PMF from CDF and vice versa. We could derive it as follows. So considering random variables that are discrete, we're going to go over a sample question. So suppose that we have 3 batteries randomly chosen from 3 new batteries. Let's denote these using drawings. So I have 3 new batteries. Say these are my new batteries. Okay, then I also have 4 used but still working. I have 4 more. These are used but still working. And I also have 5 defective batteries. 2, 3, 4, 5. These are defective batteries. And I am selecting 3 batteries here. So what I'm doing here is I'm just taking random 3 out of this group of 5 plus 3 plus 4, 12 batteries, a total of 12. We have a total of 12 batteries. So X is using a random variable. I define X is the number of new batteries that are chosen. Y is the number of used but still working batteries are chosen. So now I want to define the joint probability mass function. It's the probability mass function, PMF, which can be denoted in a table. So let's start to define it in a table. So I want to define the probability of PMF, right? Of AB, which defines the probability of X equaling A at the same time that Y is equaling B. In other words, I want to see the probability of there are A new batteries chosen at the same time there are B number of working batteries that are chosen. So let's see what possible numbers we can have. How many are we taking? We're taking 3, right? We're selecting 3 batteries. Where am I? I'm selecting 3 batteries. So in each case, when I consider my first variable, say X, so I'm considering my first variable, what possible values do I have for A? What possible values do I have for A? Let's use A instead of X. So what possible values do I have for A? A, the number of new batteries. So I'm choosing 3 batteries out of the all, and I have 3 possible new ones. It is possible that in my selection, I don't have any at all. It is also possible that I have 1 new battery. It is also possible that I have 2 and that I have all three new batteries. It is possible. Next, we're going to consider why. Why is the number of used but still working batteries that are chosen that can be any value of B. So in any case that I'm taking 3 batteries, I could end up with 0 used but still working batteries, 1, 2, and 3. Same case, right? So now we're going to compute the probabilities of each possible combination. Sorry, give me some time. It's not that easy. So in the case that I have no new batteries, and I also have no used but still working batteries. That means that I'm only taking this one here, right? I'm only taking 5 defective batteries. Which, how do I get it? So the possibilities are, I have a combination of 3 out of 5. So combination of 3 out of 5 over the combination of 3 out of 12. So the sample space, don't forget the sample space is the combination of me taking 3 batteries out of 12 total. That's my sample space. And in this particular case, I have the combination of 3 out of 5 because this is the only selection I can take, the defective batteries. I cannot take any of the, I did not take any of the new ones. I did not take any of the 4 ones. Let's move on. Now, for the combination of, let's go on to this block here. In this case, I'm taking no new batteries, still 0, and I'm taking 1 of the defective, one of the working, used but still working batteries. So I'm only taking 1. So AKA I'm taking combination out of these 4. I'm taking 1 of them times, remember our multiplication rule. If I have no new batteries, that means the remaining 2 batteries must come from the defective batteries. So here is the combination out of 5 defective batteries. I'm taking 2 over my sample space and so forth. And you may notice that, I can fill it out one by one. You may notice that this case is not possible. I'm only taking 3 batteries. So if I already have 3 new ones, there's no way I'm taking another blue one. This is also not possible, and this is also not possible. 2 and 2 is not possible. This is not possible, and not possible. And oh no, this is possible. This is possible, and that one is also not possible. This one here. So if I were to ask you, what's the probability of the sum? Let's see. Here I could write the probability of x. What's x? Yes, x equaling J, B, so x equals B. So here, x equals B, not x, y, apologies. If I wanted to find out the probability of y equals B, which is this part here, I can just sum up all of these, sum up all of these, sum up all of these, and sum up all of these. Because when I'm considering y equals B, in this case, y equals 0, y equals 1, I don't really care what x is, right? This is x and this is y. I don't care what x is, so I can just sum up all of the probabilities when x has any value. Same goes for the other way around. I can also compute the probability of x equals A by summing up each row. So I'm going to check. So this is the key, the answer that I took from the book. And as you can see that these are 0 because it's not possibly happening. And these are pre-computed combinations. You can check them one by one on your own. And when I'm talking about the row sum, that means that I'm just considering that x, here's x, this is y, remember? I'm just considering the probability of x equaling a certain number. I don't care about y. So I can just sum it up. So in that case, I can then compute this one here. What is this question? Please find the probability F. It's a big F. That means this is the CDF. What is the probability that X is less than equal to 1 at the same time Y is also less than equal to 1? What I need to sum up is this area here. Because in this case, X is less than equal than 1. At the same time, Y is also less than equal to 1. And conversely, if I wanted to find PY equals 2, this is Y equals, right? Y equals 2 is this sum over here, aka this value. So here we see that this table, although it seems meticulous to write down, if you finish it, don't forget you're allowed to use calculator to help you compute. It's quite easy to derive different types of probabilities from it. So from this joint probability, you can get the individual probabilities as well. So up until now, we're only talking about the PMF/CDF. So we're talking about discrete random variables, but we already know that this is not our only friend. We also have a joint probability density function, which is slightly more complex because you need to use the integration. So what happens when we are talking about two random variables with different PDFs at the same time? We're talking about a double integration. So in other words, when I'm trying to compute the probability of X being on a certain range and Y being under a certain range, then what I need to do is do a double integration of the joint PDF and use each, each interval as the limits of the integral. Note here that what I need to do first, like don't forget that if it's AB first, then that means it is integrating against X first, and then the next one, the outer one, is integrating against DY. Many times I've had students mix these up because of confusion, obviously, but don't forget that when you're integrating X, then you use the X limits first, and then you integrate Y, then you use the Y limits outside. So in the context of joint CDF, sorry, why is it CDF? Yes, joint CDF, as you recall, you can take it as an integral of the PDF. And conversely, when I'm trying to define a CDF from the PDF, then I can take the double integration of limits are negative infinity. Remember, because when I'm talking about CDF, I'm saying anything up to a value, so I don't have the left-hand limit, so I can just use negative infinity. Okay, sounds daunting? We have a sample here, don't forget, don't worry. So let's look at this question. So the joint density function of X and Y is given by this equation. You are asked to find Px larger than 1 and Y is smaller than 1. So as we previously denoted, when I'm trying to compute this, I need a double integration. So the first integration that I need to do is X. So let's write down the equation first. E is 2y dx. So the limits of X, so I want to compute X is larger than 1. So that means my bottom limit is 1. What about my upper limit? I don't have one here, infinity. Okay, now I'm going to integrate it against Y, or my outer integral. That means my limits are Y is less than 1. That means my top is 1. And my bottom limit is theoretically negative infinity because I have Y less than 1 and I don't have a bottom limit. However, note that this equation here, this function is only valid for x's and y's that are larger than 0. Thus, instead of using negative infinity, I can use 0 instead. So I'm going to leave that to solve later. And here, when I'm computing, what's the probability of what's fx of a? This I can translate to, this is the probability of x being less than a. Remember, it's a CDF. AKA when I have x equal than less than a, this since I only have the joint function of x and y, then I have to denote this part here as a joint probability, aka when x is less than a, at the same time y is technically larger than at any value, right? Y can be at any value, but luckily this equation is limited and is only valid from 0. So I can also say y is equal to 0. And in other words, I can denote the integral as, let's write it down again, minus 2y dx dy. And for dx, let's see the limits of x. Where's the limit of x? Less than a. So less than a, and the bottom is 0 because it's not valid under 0. And for y, it should be, the limits are larger than 0. So it should be, x is less than, y is larger than 0. Okay, so here we have, apologies, I just realized, since we're computing this, it might be easier for us to integrate for y first. Might be easier to integrate for y first, although please correct me if someone is better at calculus. I don't think it should matter, but in this case, y will be larger than 0, so it'd be starting from 0 up until limit is infinity, and for x, it will be less than a, so it'll be a and 0. And we can leave this integration. Let's see if I translate it correctly first. 1, 1, 0, infinity 1, 1, 0, infinity 1. And here it's a1. Yes. So I had correctly translated it up until this part. Here. And please remember that for the context or for intents and purposes of Statprob, actually up until here, you have already done it halfway. So you should ideally utilize your calculus in order to solve it until you can have a simplified version like this. However, it will probably only make up to half of the points of a certain question, because it's more interesting for me, it's more important for me that you know how to translate this into the correct integral and not solve the integral itself. And just now we had double integrals, and theoretically you can also compute the joint probability distribution of more than 2 random variables, and thus you can have multiple layers of integrals as follows. So the TLDR of the jointly distributed random variables can be found on this slide, in which we can define both the joint PMF, joint CDF, and joint PDF of x and y. Note that PMF is only valid for the discrete ones. PDF is only valid for the continuous ones, while CDF can be used for either. So we also have independent random variables. Remember, we also had independent events, and we showed that if the probabilities of both of the union equals the product of the individual probabilities, then they can be denoted as independent. Same goes for random variables. If discrete, then the probabilities of the product of the individual probabilities, if they're equal to the joint PMF, then yes, they're independent. And if they're continuous, then we use the PDF. So you use either the PMF for discrete or PDF for continuous. And if they fulfill this property, then you can say that they are independent. If they do not, then they are not independent. However, you may have a feeling like when we showed the examples last week, it was kind of strange, right? It should be independent, but why aren't they? Or they should not be independent, but they are. So regardless of what you may have intuition for, if they fulfill this equation, then they are independent. And once again, it's also extendable to more than 2 random variables. And finally, conditional distribution. Oh, here is our friend. This is our friend, remember? PE given F. P equals PEF divided by PF. Please don't forget this friend. This friend is going to be coming up a lot. So even using random variables, it is the same. Watch here. What's the PMF of X given Y? It equals the the probability of X given the probability of X equals a value given Y equals a value equals the joint probability on top divided by the probability of Y, since Y is the sample space. And we end up with the same type of formula that we already were introduced to. And that goes as well for the conditional distributions of a continuous random variable. The only difference is that it's denoted using an F and not a small p. So here we use a here we use the PMF, and here we use the PDF to define the conditional distribution.